Saxon Algebra 2, Lesson 66. My camera's working. I'm recording. I'm hoping nothing goes wrong. This one has two parts. The first part is kind of a little housekeeping detail. The second part is really cool. And we're going to talk about it for a long, long time in our lives. Add. Let's say that we're happily working along in our algebra homework and we come across this problem. Now, it's telling us to add. We see here that we have fractions, or as we like to call them now that we're further along in algebra, rational expressions, and we see that the denominators are unequal. And we know that in order to combine these, in order to add them, we need our denominators to match. And so we're looking at these and we realize, well, we've got the right letters. The signs are just mixed up. So what the idea with this lesson is that we can change the signs down here to make them match. And here's the way that we do it. We don't want to pay any attention to that minus sign there. We're leaving that alone. What we want to do is multiply top and bottom by -1. As long as we multiply top and bottom, we're fine, right? So let's do that. This stays the same over here. That minus sign stays the same. This becomes minus 7a over positive x minus 3. So the moral of the story here is that the numerator has a sign, the denominator has a sign, and out in front of the fraction, there's a third sign that lives there. And we can manipulate those for our own greater good. Okay, what you just have to do is make sure that you're intentional about which ones you're doing. When, here I'm changing, not that one, I'm changing this one and this one. And this, because it's a binomial, I had to distribute, right? All right, now I can combine those two. So I get 1 over x minus 3 plus 7a over x minus 3. And that equals 1 plus 7a over. Make sense? So this is kind of like a little specialty problem that we're troubleshooting this particular kind of scenario that you can solve. And let's do one that's slightly more sophisticated. For some reason, John's really stuck on this x minus 3 thing. This time, instead of flipping the signs, he flipped the order, which does the same thing. But again, we see, if we want to add these, we have to have matching denominators. They're close, but there is not a cigar involved. But by just affecting the signs of these, we can get the way we want it. So we don't want to affect that, but we want to multiply top and bottom. And these are both binomials, so we have to be careful with that. Okay, so the first part stays the same, 4x plus 5. Plus sign in front, okay? Then we're going to have minus 2x plus 3 over, and now I'm going to reverse the order. The x is going positive, the 3 is going negative. Okay, this time we have a plus sign here. So that doesn't change any of these signs, right? Last time we had a negative, so it flipped the sign on top. This time we have a positive, so we don't have to deal with that. We can just combine everything into one fraction now. 4x plus 5 minus 2x plus 3. Notice that we already fixed this sign, right? So everything's cleaned up there. And this will all be over x minus 3. And then we can combine like terms. 4x minus 2x and plus 5, I'll put those in triangles, plus 3 is plus 8, all over the quantity x minus 3. Final answer. Yay! So when we want to, we can manipulate the minus signs in a rational expression. We just have to be careful the way that we do it. We leave the joining sign alone, and we change the signs of the numerator and denominator. And then, if necessary, we combine those together. It's a little tricky. It's kind of a special case scenario, all right? But the way I always think of it is you're just multiplying top and bottom by -1. All right, let's change gears. Oh, good, I'm still filming. I'm paranoid now, so paranoid. Okay, part B. This is a friend that you're going to hang out with for probably the next 1.5 years of your math life. And here's the thing. When we are doing trigonometry, we have learned that there's a lot of information stored in your calculator, and you can find sine, cosine, and tangent of just about anything, any angle you want, by plugging stuff into your calculator and hitting the right buttons. Now that's great, but you know me, and John's the same way. We prefer to keep our hands off the calculators, because once you start pushing buttons on a calculator, you forget about what the math is actually doing, and you're just thinking about how to push the buttons, right? It happens to me all the time. I stop thinking about the math, and I just think about the dang buttons. So we're going to get our heads out of the calculators and do more of our trig work without needing calculators, okay? It's going to be so much easier. And there's 2 triangles that we're going to memorize, don't worry, they're simple, that are going to give us a whole bunch of information that we can use to do those calculations without needing our calculator. The first one is the 30, 60, 90 triangle. And draw it with me. What we're drawing is an equilateral triangle. I'm trying to make it so all 3 sides look the same and all 3 angles are the same size. I've got it facing like a backwards play button, right? It should be the other way if it's an actual play button, but I want it to point the way I've got it, so do it my way. I'm so bossy, right? Do it my way. And we can say that each of these are 60 degrees. Might not look like it, but they are, okay? Now, we know that an equilateral triangle will also have all the same size lengths, right? Instead of making them all 1, that would be the simplest thing, but you'll see there's a method to my madness. We're going to imagine each of these as being 2. Okay? Now, what we're going to do is we're going to chop it in half. Let me show you how. We are going to take it and chop it like this down the middle. Pretend that's perfect. Okay? That creates a new triangle that looks like this, right? And I'm going to draw that over here. This angle up here is still 60 degrees. We didn't impact that. This angle here is now half of what it was. It's now 30 degrees. And this angle here now is a right angle, so that's 90 degrees. Do you see how we cut this simple, regular, equilateral, equiangular triangle in half and came up with something new? And let's see what happened to the sides of it. This one's the same. This long one, they're all the same length, so I shouldn't say that, but this one got cut in half. So this is only 1 instead of 2. How long is this side? I don't know. We don't have a length on that. Let's use Pythagorean Theorem to figure it out. Here's a leg, and that's the hypotenuse. So I'm going to call this x. And I'm going to say x squared plus 1 squared equals 2 squared. X squared plus 1 equals 4. Subtract 1. X squared equals 3. So x equals the square root of 3. This gives us a triangle with a 30-degree angle, and if we want to find the sine of 30 degrees, okay, the sine of 30 degrees equals, let's see, sine is Oscar head, right? These are called trig functions. Right? That's what this is called. Oscar had 30 degrees. The opposite is 1. The hypotenuse is 2. The sine of 30 degrees is 1/2. No calculator button pushing needed. If we want the cosine of 30 degrees, okay, that's a hold. Cosine is the adjacent, so that's square root of 3 over the hypotenuse of 2. And if we want the tangent of 30 degrees, that's over Arthur, right? The opposite is 1, and the adjacent is square root of 3. Beautiful. This one, though, we could rationalize because we don't want a square root in the bottom. So that would become, we'd multiply it top and bottom by square root of 3. So it would be square root of 3 over 3, right? So see, we can calculate the trig functions off this triangle really easily. But here's even better news. It's not just a 30-degree triangle, it's also a 60-degree. So what happens if we reorient ourselves up here? The sine of 60 degrees, again, that's opposite over hypotenuse. From here, the opposite is square root of 3. Opposite over hypotenuse is 2. The cosine of 60 degrees, that's adjacent. From here, the adjacent is 1. Hypotenuse is still 2. And the tangent of 60 degrees, that's over Arthur, right? That is opposite square root of 3 over 1. Or we could just say square root of 3. So, not only can we calculate all three functions for the 30 degree, but if we flip our perspective, we can calculate all three functions for the 60 degree. That's 6 different trig functions we can calculate by just looking at the dang thing, right? It doesn't really require any work. The worst we had to do was rationalize this one. The other thing that's interesting, if you notice it, we're not going to talk a lot about this yet. We're going to start using this triangle to do calculations, and we're going to do that in just a hot minute. But look what happens. The sine of 30 degrees is 1/2. The cosine of 60 degrees is also 1/2. The cosine of 30 degrees is the same as the sine of 60 degrees. And the tangents are reciprocals of one another. Huh. Interesting to think about, isn't it? I wonder why all that is. Don't worry, we're going to get to it. So I'm going to draw this one more time, and I want you to draw it with me on this page. What I like to do is I imagine the whole equilateral triangle first, but I only draw the part that I want. But I remember, okay, this is the triangle that this was the angle that wasn't touched. This was the one that was chopped in half. This is what became the right angle. This was the original size at the full 2. This is the side that got chopped in half. That's the 1. And then this was the one that we had to calculate. And here's how I remember it. 1, 2. This is 3, but it's the square root of. There it is. There's our 30, 60, 90 triangle. And with that, we can do all kinds of interesting problems like this one. Use similar triangles to find x and y. Okay, so let me draw for you. This is not the kind of problem we're going to be doing a lot of, but it's just a kind of a baby step into this. John gives us a triangle that looks like this. Yikes. Pretend it's straight. That's what he gave us, okay? And he says use similar triangles to find x and y. What? What is he even talking about? I thought we were talking about trig functions. Well, we are, but we can use these triangles for even more. Now, I notice here's a 60 degrees and here's a right angle. That's the same as this. So what I'm going to do is I'm going to redraw my reference triangle. That's what this is called. It's a 30, 60, 90 reference triangle. This obviously refers to the 3 different angles in it. Reference means we refer to it to do lots of other problems. So what I'm doing is I'm redrawing it just so I can compare it to this one more readily. So I know this is my 60 degrees, this is my 30 degrees, this is my right angle, and then let's see, this would be 1, and the straight back is square root of 3, and the hypotenuse is 2. Okay, so what I've done is I've just kind of flipped this around in my head and redrawn it so I can compare it. Now we're ready to just use proportions to solve similar triangles, which I just taught the Algebra 1 halfers to do. The Joel, Alexis, and JoJo crowd just learned how to do this. Oh, I'm still in my green pen, even though you guys are the reds. Oh well, pretend. It makes you feel smart because that means you're next year. Okay, so what we do, again, when we have similar triangles is we look for the anchor proportion. It's 5/2. I always put the left triangle on top and the right triangle on the bottom. And then we just look for other pairs of sides. Let's do x next. X partners with square root of 3. So all we have to do is cross multiply and divide. We get 5 times the square root of 3 equals 2x. So we get x equals 5 times the square root of 3 over 2. It's not a particularly pretty answer, but that's correct. John does it with scale factors. Don't listen to him. John also draws his reference triangle differently. Don't listen to him. Do it my way. It's better. Okay, and then we use our anchor proportion again to solve for y. And y partners with a 1. Okay, so we get 5 times 1 equals 2 times y. Y equals 5 halves. So our reference triangles can be useful for more than just trig problems. We just used it to solve to find the sides of a similar triangle. All right. I want you to start memorizing this, but honestly, if you remember how we drew the pictures to create it, you will teach yourself how to memorize it just by going through this process in your head. And if you feel like it's still not quite making sense, right now, before you even get up and go do your homework, try copying this over again. Start with the triangle, 60 degrees in each corner, 2, 2, and 2. Then chop it in half and see what happens. Okay? That goes to 30 degrees. That gets cut in half. It's now 1 instead of 2. And then we can do a quick Pythagorean to solve for the third side. All right? If you can remember how to do that, this will just naturally come. Okay, I'm going to stop talking now, and I'm going to leave you to enjoy this lovely lesson. Thank you, and goodbye.